Hello, my name is Marcus Friedel, and I'm presenting PantographHaptics, a technique which uses a pantograph mechanism to passively render large objects and surfaces. We together are working towards delivering tangible user interfaces, ubiquitous computing, and embodied experiences that are outside our physical and social realities. PantographHaptics focuses on a small, important piece of that goal: stiff interactions with the walls, desks, and grounded objects that give physical context and foundation to virtual environments. Existing devices, full-size proxies, robotic force rendering systems, and locking devices each have drawbacks such as lack of portability, impedance during free movement, limited stiffness, or locking in place. PantographHaptics, like locking devices, is able to provide transparency and high stiffness by generating the reaction forces solely through mechanical members, rather than directly via motors. But like proxy systems, PantographHaptics also provides encountered interaction, allowing the user to freely explore the entire render. The technique can be conceptualized as a proxy-based system that uses a miniature version of the object instead of a full-sized one. The pantograph I am referring to is not Hayward's active force rendering device, but rather the classical mechanism historically used to create scaled copies of graphics and designs. To apply the pantograph for haptics, a user drives the large-scale path, the pantograph miniaturizes the user's motion, the system constrains the small-scale path, and the user perceives the constrained motion as a mid-air surface. Pantographs are fundamentally planar, but can be extended into 3D by the addition of a revolute joint at their base. Our grounded implementation, HapticLever, validates and demonstrates the key PantographHaptics interactions. The user is able to move the interface node transparently, without friction or resistance while in midair, is able to freely encounter the surface and receive immediate stiff reaction force generated only through the mechanical members, is able to slide along the surface with their entire range of motion despite the small size of the constraint platform, and then is able to disengage from the surface without the system changing state or engaging or disengaging any locks. With HapticLever, we show how the rendered constraint can be dynamically reconfigured while preserving the high stiffness and passive force generation. By using self-locking lead screws, torsion from the motors is able to drive the system, but axial force from the user is resisted by friction between the nut and the screw, and so the user is unable to backdrive the motor or displace the platform. While flat planes are easiest to demonstrate, this technique can render a variety of shapes and surfaces, demonstrated here by placing various shaped obstacles in the path of the constraint node. Ultimately, using a shape display device as the constraint would allow for the greatest versatility. You will note that because the pantograph mathematically traces an infinitesimal point, the finite size of the contact sphere causes a slight offset between the intended geometry and the traced path. This can be addressed through thoughtful design, but otherwise can cause rounded corners or omit some concave geometry. In a comparative evaluation, users praised the force response of the device, but they noted the inertia of the arm when accelerating or changing directions and agreed that the pinched handle lacked the rich palm and multi-finger interaction with the table that they expected. We also present Feedbackpack to validate the concept's portability even with higher degrees of actuation. Feedbackpack again demonstrates the core characteristics of PantographHaptics: free motion and free space, ability to freely encounter, engage with, explore, and disengage from the render, and immediate stiff force response generated solely through mechanical members. Feedbackpack's 3 linear and 1 rotational degrees of actuation allow it to provide dynamic application-based rendering and also enable movement compensation for when the user walks around. Because Feedbackpack is worn, whenever the user walks or turns, any rendered objects or surfaces must move in opposite and equal displacement relative to the user. Unlike active robotic force rendering devices, Feedbackpack's pantograph-based lead screw-driven system is able to provide very high reaction forces and perform movement compensation without risk of injuring the user. In addition to using direct contact between the constraint node and an obstacle in order to constrain the path of the pantograph, Feedbackpack also demonstrates a pinched rod method, in which a rod is attached to the constraint node through a universal joint, and the rod is constrained to move in a plane by being pinched at 3 points. The pinched rod method is more compact and allows easier rotation of the render angle, and does not suffer from the same contact offset issue mentioned earlier. Despite Feedbackpack's size, users reported that the ergonomic backpack form factor was not burdensome to carry. The workspace of the actuation system, and therefore the size of the device, can be further reduced by engineering the device to tighter specifications and using stronger materials to enable a more extreme scaling factor for the pantograph, leading to a smaller workspace volume of the constraint node. The potential for such further engineering improvements is evident from the design refinements made between the HapticLever and Feedbackpack prototypes, such as passive gravity compensation of the arm with springs and a more ergonomic handle, both of which users reported in the user evaluation increased comfort and realism. In the first user evaluation, participants performed a timed task with HapticLever and 3 other haptic modalities and provided the qualitative feedback summarized earlier. In the second user evaluation, participants performed a distance recognition task with Feedbackpack and gave qualitative feedback on the device's wearability and interaction fidelity. For more details, please see the paper. These 2 implementations validate that PantographHaptics supports transparent motion as well as stiff and encounter type interaction with large surfaces without requiring a full-scale proxy. As a tool in the force feedback toolbox, PantographHaptics' niche is in applications where the surfaces are simpler rather than more complex geometries, where the surfaces do need to be dynamically changed but aren't constantly moving, and where the interaction with the surface needs to be stiff and requires frequent engaging, disengaging, and sliding. This encompasses the likes of drawing canvases, mid-air UI panes, and even invisible armrests to prevent arm fatigue. As mentioned earlier in the context of the implementations, the inherent limitations of PantographHaptics are that it renders an infinitesimal point at any given time, rather than providing rich, whole hand interaction, and that the arm adds weight and inertia that are not present in real and proxy interactions. Because of the point rendering, users interacted with HapticLever and Feedbackpack by gripping a handle, just like most active force rendering devices. But if in the future we look beyond direct hand rendering, PantographHaptics is even more promising for pen interactions, where the render point is at the pen tip, for mid-air hand stabilization interactions, where the render point is on the side of the palm, for docking haptics applications, where it is used together with, for example, a glove, or where 3 pantographs are used together and their render points define an encounterable plane. The issue of arm weight and inertia can be mitigated to a large degree through good engineering, employing passive gravity compensation and designing the links with low mass and high moment of area. In the long term, I expect that immersive simulators will take the form of locomotion devices paired with grounded, encountered robots. For now, I am pleased to contribute PantographHaptics, a force feedback tool that can safely provide configurable, transparent, stiff, encountered interactions with virtual surfaces without requiring a full-size proxy. I am happy to answer questions.